In this part of the tutorial, I will talk about monads and semimonads. This continues the consideration of how we can do computations in a functor context, or in Scala this is the functor block or the for yield block. In this part, I will concentrate on practical issues. The first example we will use is this computation. In this computation, we need nested iterations. In the functor block, nested iterations are expressed with several left arrows, or they're called generator arrows. So the program for this computation can look like this. On the left, I show it in the functor block syntax. On each line, as you see, the generator line gives you an iteration. I goes over this sequence from 1 to n, j also goes over the same sequence, and k goes over the same sequence, and they all go independently. So for each I, j goes over all of these, and for each I and j, k goes over all of this. And in the yield expression, we compute this function f that we're supposed to compute here, and the result of this sub-expression up to this parenthesis is a large list of all values of f for each choice of I, j, and k. And then we take a sum of this large list. So that computes the sum in this expression. If you replace the left arrows, as the Scala compiler does, through map and flatMap, then you will see that the map replaces the last left arrow, and flatMap replaces all other left arrows, or generator arrows. And so line-for-line translation of this code could look like this. So instead of this syntax, we have this. Instead of this, we have this, and so on. And you see how this works. So the last expression is just a simple map, because we just need to compute the value f for each of these k's. But this result is a list. And so the argument of flatMap is a function that takes j and returns a list. The result of the flatMap is again a list, which is this one, up to this brace. And this is the body of this function, taking I as the argument and returning this list. So again, the argument of flatMap is a function from a value to a list. So this syntax is available for the sequence functor, because sequence has flatMap defined in addition to map. If that functor has a filter defined, or the function method is called with filter, as we have seen in the previous tutorial, then we can use the if lines in the functor block as well. In this tutorial, we will occasionally see the if lines, but we concentrate on what happens when you have several left arrows. It is named flatMap because it is actually equivalent to first doing a map and then doing a flatten. How would that work? Well, this code, where the function in the brackets or in the parentheses here takes a j and returns a list, the result of that would be a list of lists. And when you flatten that, you get a simple list. And that is the same as doing a flatMap. So functors that have flatMap and flatten defined in them, I call them flattenable, or semimonads. This is my own terminology. Flattenable and semimonads is my terminology. There's no accepted name for these functors. You must have heard of monads. Now, monads are more than just functors that have flatMap or flatten. Monads also needed an additional method called pure, which has this type signature. However, this method cannot be used in the functor block directly, so it does not correspond to a specific construction of a functor block. Of course, let me correct myself, it can be used in the functor block as any other method, but it has to be used here on the right hand side, because here this an arbitrary Scala code here, so you can use any methods you want, but it is not special to the functor block. It does not have a special meaning. And also, we will not need this method much. In fact, it is not very often used. Other methods are more important than pure. And so, mathematically, adding the method pure makes an interesting mathematical structure, but for the practical use that I'm going to talk about, this is not very important. So, full monads or monads are functors that have flatMap and pure with appropriate laws, which I will talk about in another part of this tutorial. Semimonads are those that just have flatMap, and they may or may not have pure. In many cases, they will also have some natural definition of pure, but in some cases they won't. So let's concentrate therefore on semimonads, or monads that don't have pure necessarily. Let's look at more visual example of how flatMap works with lists. So consider this expression, how we would compute that expression. So let's assume that the function f takes a value of x and returns a list of some values of type y. Now, if you have specific values x1, x2, x3 here, then the result of applying f to them might be a different list each time. It could be even a list of different length with different values inside. So let's imagine this is the result of applying f to x1, x2, and x3. So the flatMap will put all of these values together in one list. If we first do map and then we do flatten, then what happens is that the map will replace each of these x1s with its corresponding list. x1, x2, x3 will be replaced by these three lists. So that would be a list of lists of y. Then you flatten that, and then you get a simple or flat list. Let's develop some more intuition about what happens with data in a functor or in a collection or in a container when we use flatMap or when we use several generator arrows in a functor block. So here is a schematic example of some code that tells you that I goes over this collection or container or sequence in this case. J goes over here. Then we compute some x as a function of ij. Now at this point, we have computed a whole sequence of x's for each I and j, a different x perhaps. Then for each of those x's, we still have another nested iteration. And then we compute some y as a function of I, j, and k. And actually, at this point, we have computed a large list of y's of perhaps different values of y, different for each I, j, and k. And then we compute another function h of x and y. So this entire result will be a long list of values of this h computed for each I, j, and k, a different value of h. So this code is a translation into a non-functor block syntax. So you see line for line, same thing, 1 to m, 1 to m, I, 1 to n, 1 to n, j, j. So this is here x equals this, here we need to say val. In the functor block we don't say val. That's the only syntactic difference. So 1 to p, 1 to p, k, k. So here we have this line-by-line translation. This code computes exactly the same value of the result, which is going to be a list of values. So one thing we notice is that every line that is a generator line, that is, every line that has a left arrow, must have a same type of container on the right-hand side. So this is a list or sequence in general. In this case, this is going to be subclasses of sequence, some vector or something like that. Each generator line needs to have the same type. We could not, for example, here use sequence and here use some completely different container, such as, let's say, tree or something like that. We couldn't do this. It must be the same type. And this is so because flatMap is defined like this. flatMap requires that this sequence type is the same as the sequence type returned by this function, which is all of that. So all of that should be a sequence of the same type as this. And so for this reason, each container or sequence or collection on the right-hand side of a generator arrow must have the same type, same container type. Another thing we know is that each generator line actually starts an expression. So if you look at this generator line, for example, the j, the translation of this actually is this. So j goes to that. So this entire thing is an expression that evaluates to a list, to a sequence, which is again a container of the same type. So you can think about this syntax as nested computation, where each line starts a new computation, yielding finally the value of the same type. Let's now look also at the number of resulting data items. Now, I goes from 1 to n, j goes from 1 to n, k goes from 1 to p. So in this case, clearly we have m times n times p different elements in the resulting list here. So this will be m times n times p values in the result. If we had some other code here, for example, if this were not from 1 to n always, but the length of this sequence were somehow a function of this value I, let's say, then we would probably have the different number of data items depending on the data. Or we could have fewer data items because we could have an if line which would filter out some of the data, so we'll have less than m times n times p. But in any case, we could have up to m times n times p resulting data items in their container. So the container type that we need for this kind of computation is at least such that it can hold m times n times p items if it can hold m items or n items or p items. So if we ask the question, what kind of containers can have flatMap? In other words, what kind of containers would fit this style of computation? The answer is at least this type of containers must be such that if the container can hold m items of data and it can hold n items of data, it must also be able to hold at least m times n items of data. So the capacity of the container must be closed under multiplication. In other words, the set of all possible capacities or capacity counts of the container must be closed under multiplication. This is an interesting property. What container types have this property? So for instance, a sequence or a non-empty list. These containers can hold any number of items. In the case of non-empty list, any number of items that's at least 1. So that set is the set of all integers at least some minimum. That set is certainly closed under multiplication. And also, well, it's not just multiplication, it must be closed under this. It must be, if it has m elements and it has n elements, it should be able to hold less than m times n elements, any number of pretty much elements less than that. So obviously sequence and non-empty list are such containers with this property. Another important example of such containers is the containers that can hold only 0 or 1 elements. For example, option is such a container. Option can hold 1 data item, or it could be empty. Either is another such container that can have a data item, or it can have some error message string. Try is another such container. It could have a data item, or it could have an exception. Future is another such container. It holds a data item that is going to be available in the future, or it could fail also, fail to compute that item. So these I call the pass-fail containers. These could hold at most 1 data item. And clearly the set of capacities for this container is a set of two numbers, 0 and 1, and this set is closed under multiplication. Another example of a container that would have this property is a tree-like container that must have, for instance, 3, 6, 9, 12, and so on elements that are always multiples of 3, let's say. So it branches in such a way that it can only hold the number of items that's a multiple of 3. And obviously this kind of set is closed under multiplication. Finally, there are several containers that I will also talk about, which I call non-standard. Examples of such containers are these. So these are functors, because here A is a covariant position. Here also A is in a covariant position because it's behind 2 arrows, 2 function arrows. So these are functors, but they're not really containers with data in an ordinary sense. There's no way in which you can say they hold 5 or 11 items of data or something like this. They hold data in some non-standard way. And we will talk about the usage of these containers and give examples. But these also, in certain cases, so certain function types like these also can have flatMap defined on them in a reasonable way. So let's look at examples now. The first set of examples are what I call the list-like monads. So, by the way, all these examples here are monads. They're not just semimonads. But we will just look at the flatMap, and so we will not use the fact that they are full monads. So for us, it's not really important to make that distinction right now. We only focus on flatMap. So what are the typical tasks that list-like monads perform? Typical is make a list of combinations or permutations. Go over these, filter out what you want, and get a list of results. So that's a typical computation of this kind. Another situation is that if you have some problem that has many possible solutions, you organize these solutions in a solution tree, and you traverse this tree with, say, a recursive depth first search, and then you again filter out solutions that are incorrect, and then you get your resulting solutions. Now the containers that have this property may be eager sequence, so eager means all elements of the sequence are computed up front before you can use the sequence, or they can be lazy, which so iterator is one example, is a sequence whose elements are not all computed up front. You can already start using the iterator, and as you need, it will compute new elements. So that's called lazy computation. Stream is another data type in the Scala standard library that computes lazy values. So it does not compute upfront all the values in the stream. It computes them when you need to do so. And once you have computed them, they are stored in memory, but until then they are not. So these are eager and lazy evaluation strategies. But the way you write code is very similar. You just have flatMap defined on iterator, you have flatMap defined on stream, and so you can just use them. Usually, list-like containers have a lot of additional methods defined in them. It's a very rich data structure. So they're monads, they have pure method defined in them. I'll just remind you that the pure method has this type, so it just takes one data item and creates a container that has this one data item inside. So clearly you can put one item in a list or an iterator on a stream and so on, that's clear. But many additional methods are used, such as appending lists, prepending elements to list, concatenating lists, fill, so you make a list that has certain pre-computed elements, fold, scan, and those are methods that are all defined on these list-like monads. So actually, program code mostly uses methods like these and not pure. So it is not very important for programming, for the practice of programming, to have the method pure defined on list-like monads. And actually it's the same for most monads. The method pure is quite secondary in its importance for practical programming. Let's look at some examples. So I have prepared working code in the repository. So let's take a look. So here is the first example, how we compute things in a functor block. What we want is to compute a multiplication table. So the result should be a sequence of strings such as these. So these strings need to be computed in this order. So notice that the multiplication table is only half of the matrix. We never compute, for example, 3 times 2. We already have 2 times 3. That's sufficient. And so to organize this kind of computation, we write this. So I goes from 1 to 5, but j goes from I to 5. So this is an example of the collection in the right-hand side of the generator line. And the collection is a function of the value that we defined in the previous line. So this collection is a function of I. So this is an example of having a different list here each time. For each I will be a different list. And that's fine. This is just as easy to do that using the functor block with the monad. So what do we yield? in other words, for each I and for each j, what do we compute? Well, we compute the product of I and j, and then we print this line, I times j equals product. So that will produce a string, and the whole result will be a sequence of these strings. So we have a flat sequence, so to speak. Remember this heuristic or mnemonic choice of the name flatMap. So we have many nested iterations here, but the result is a flat sequence. So this test verifies that the result is this multiplication table. Here's how we can do the same using a filter. So here we do not make this second sequence depending on I. They're both the same, but then we filter out by the condition that j must be not less than I. So then we can compute product here. That's completely equivalent in terms of results. And we yield this. So this is a perhaps slightly different and maybe easier to understand way of computing the same thing. So it still computes the same multiplication table as we had here. I already ran all these tests, they all passed, so I encourage you to download this and run as well and play with it. To save time, I will not run tests, but they all pass. Another important thing here is to notice that if one of the generator arrows returns you an empty sequence, then remember this size of the result is a product of sizes of these sequences, and this sequence is of length 0. And so the resulting sequence will be of length 0. It will be empty. So just having one of these generators produce an empty sequence will kill the entire computation. It will make an empty sequence out of the entire computation, regardless of what you do here. Before or after, it will just completely collapse everything into an empty sequence. That is also an important property of the monadic computation. Let's now go through our worked examples in that slide. The first example is to compute all permutations of the sequence of 3 strings, A, B, and C. So how do we compute that? Let's just write code like this. So first we define this sequence xs or x's. Now, obviously, we need to iterate over it in some way to get the permutations. So let's do that. So let's say x goes over all this. Now, once x, let's say, is a, we need to go over the result, over the remaining elements. So let's compute the remaining elements here. So diff is the library function that computes the difference between 2 sequences, or it removes elements from the second, elements that are in the second sequence are removed from the first sequence when you do diff. And so the remain will be BC, for instance, if x is A. Then we go over the remain and we find the next remain, so remain 2, which is now all the rest, and z goes over remain 2. So now we know that it's a sequence of 3 elements, so we know that remain 2 is going to have just 1 element left. So that's what we want. And the result is we yield a sequence of x, y, z, and so this is going to be computed for each choice of x, y, and z. So the result will be a sequence of sequences. So let's check that. Control-Shift-P. Right, so that's a sequence of string. That's the result. We check in this test that the permutations are correctly computed. The standard library in Scala already has a permutations function. It's just that the permutations function returns an iterator, not a sequence. So we convert it to sequence in order to run this test. If we didn't convert it to sequence, then we couldn't compare our sequence of sequences against an iterator. The iterator doesn't have the values computed yet. Cannot compare something that already has all the values computed and something that doesn't. We need to run that to compute all the values. So that's what the toSequence does on an iterator. The second example is to compute all subsets of this set. Now, subsets of the set is not the same at all as permutations of a sequence. For instance, empty set would be a subset, or a set of B alone would be a subset, or a set of B and C would be a subset. But there's no difference between the set of B and C and the set of C and B. So all subsets is very different from all permutations. Let's see how we can do that. So let's think about it. So first, the subsets could be empty. So we need to allow empty set. The subsets can be also non-empty. So let's allow that as well. So we say XA would be of type set of string. And so XA would go over either an empty set or a set of A. So in this generator line, the right-hand side is a collection, or in this case it is a set. And the set contains two elements, an empty set of strings and a set of single A. So XA would be either empty set or a set of A. XB would be similarly either an empty set or set of B. XC will be either empty set or set of C. And then we will concatenate all these sets. Now when we concatenate sets, equal sets would collapse into one. And so the result would be empty set will be present once, then will be a set of A together maybe with empty or together with set of B. So in this way we have 8 combinations that we need. So either each of the XA, XB, and XC goes over 2 possible values, and so the result is 8. So 2 times 2 times 2 different sets. So indeed, we have a standard library function subsets that returns an iterator. We convert that iterator to set, and the result is correct. So it's all subsets of this. The next example is to compute all subsequences of length 3 out of a given sequence. So subsequences are not necessarily elements that are next to each other in the sequence, but they must be in the order. So let's look how we can do this. So here's an example. We have a sequence from 1 to 5, and the subsequences of length 3 out of this are listed here. So it's 1 to 3, 1 to 4, 1 to 5, 1, 3, 4, and so on. So how do we compute such a subsequence? Well, we start reasoning by what kind of generator lines we should write and what kind of filtering we should do. That's the way that this kind of code is written. We use the library function tails, which is a useful function. It saves us work. What does it do? It takes a sequence and it computes the sequence of first the initial one, then the tail of the sequence, then the tail of the tail, then the tail of that, and so on, until we get an empty sequence. So XS is going to be a sequence of these ranges. We filter out the nil, and then we know then that it's not empty. Actually, we filter out not the nil, we filter out the case when this entire tails is empty, because it could happen. What if we're given an empty sequence here? Then this entire tails sequence will be empty. So we filter out non-empty, we take the head, and that's the first sequence here. And then we take the tail of that, so the tail of XS is these. And that's our remain one. So now we go over the sequences in these, in the tail of XS. So let's say first of one would be these. Again, we filter out that it must be non-empty. Take the head and then take the tail of that. And what this does is that in the next iteration we would have X going here, Y being here, for example. And so that's how we find all the possible subsequences. So we can take this, this, and this, and taking heads of those would give us 1, 3, 4, or 1, 3, 5, and so on. So this is the way we produce the subsequences. This is a bit manual. There's a lot of boilerplate code, but this is the code that kind of is obviously correct. We take the tails, then the other tails, and so on, and it works as expected. So you see we have used if, we have used non-generator lines, or the computation lines, which are map. These are flatMap, and this is a filter. So we use all of the features of the list, as we should. We should always use all the features if they are helpful. So this code computes the sequences we expect. The next task is to generalize all these examples to support arbitrary lengths instead of 3. So here we had hard-coded length and hard-coded length 3. Now we want to generalize, and this is of course a little more challenging. But notice in all these code examples we had really hard-coded the fact that we are looking at length 3. Let's see how we can generalize this. It's not a lot of work. It just needs to be a little more clever. So let's look at the first example. The first example is permutations. Well, obviously, we still do the same thing as before. Let's take our code for permutations, see what we do. So we do X going through this sequence, and then we compute the remaining subsequence, or part of the sequence, by removing the X we just chose. So the result is a smaller subsequence, and let's just use the same function to compute the permutations of that recursively. So that's the idea here. So we take x going to over all the x's, compute the remain, and then the y's is going to go over all the permutations of remain, and that is a recursive call to the same function. So y's is going to be a sequence of elements, because the function returns a sequence of sequence. So since on the right hand side of the generator line we here have a sequence of sequences, the left hand side will become a sequence. Now notice the generator line has to be the same container type sequence. It doesn't have to be the same element type. So in the first generator line, the container type is sequence, the element type is A. And here, the container type is sequence, the element type is sequence of A. So that's fine, as long as the outer container type stays the same. Now, this variable is going to be sequence of A. So we need to append x, which is the first element we chose, and the permutations of the other elements. So the result is that we yield this sequence, and the total result is going to be a sequence of these sequences for all x's and for all permutations of the remainder. And that's what we need, except we have to add this check at the very beginning, because we will eventually call the permutations on an empty sequence here, and we need to not break when we have that. So that's how it works, and now we can have any length and it works. So let's see how example 2 is generalized. We look at the code in example 2, we see we need to basically repeat this n times. We repeated this line 3 times here, but now we need to repeat this n times instead of 3 times. So how do we do that? We use recursion, of course. So the first line we can continue as before. Then we do the remain, which so the minus here is the operation defined on sets that removes elements from a set. Well, it doesn't really modify the set, it just computes a new set that has one element fewer, possibly. Then we do the recursive call of subsets on the remain. That gives us a bunch of sets. So for each of those sets we have a YAs, and we concatenate the sets. So it's a very similar thing, very similar idea. So we do one step that we did before, and then we call recursively on the remainder. And that works for any length of the set. Example 3 is a bit more involved, but it's exactly the same procedure. In example 3 we had this kind of code repeated 3 times. X going to sequence something tails, if non-empty, get the head, and compute the remained. Take the tails, if non-empty, get the head, compute tail. Get tails, if non-empty. So that is going to be repeated. So we're going to write this once, and then do the recursive call. So that's how this works in generalizing our example 3. So again, we need to check for empty sequences, and that's a little involved. I won't go into details here. I encourage you to look at it yourself. The main computation is here. Notice I have to put parentheses around the 4 because I need a toSeq on it. And you cannot just do a toSeq after this brace. That is not right syntax. This brace is part of the yield expression, and so you wanted to seek on the entire for yield block. You have to put parentheses around it. Right, so this is our code that we have to do. Go into tails, non-empty, get head, and find remainder. And then we do a recursive call. Now notice the recursive call is on n-1, because now the task is to compute n element subsequences of a given sequence. Now we compute n-1 element subsequences, and sometimes this n would be 0, sometimes the remainder will be empty. So we need to check both of these cases separately. So that's how it works, exactly the same. Test passes. The next example is the well-known 8 queens problem. 8 queens is 8 chess queens on a chessboard, and you need to find all locations for the 8 queens so that they don't threaten each other. The queens on the chessboard threaten each other if they're in the same row, in the same column, or on the same diagonal. So let's first write a function that finds out whether queens threaten each other. So on the chessboard, it is clear that each queen must be in a different row. If any of the 2 queens are in the same row, they threaten each other. So we'll just take a shortcut, and every queen will be in the next row, always. And the only question is in which column it is. So the integer coordinate here is a column, and these are columns, and we assume that they're all in consecutive rows. So this function will compute the condition that some queen in this position, in this column, is not threatened by any of the previous queens given in the previous rows with columns specified here. So that is when x is not the same as other x, so they're not in the same column, and when they're not in the same diagonal. So diagonals are computed by differences, row minus column, and row plus column. So these are the 2 diagonals. Alright, so now how do we find all solutions of the 8 queens problem? So here's a straightforward code. Just to be quicker, let's say the row is the set of indices, 0, 1, 2, and so etc. 7. Now x1 is the column of the first, or maybe row, let's say it's column. I want to say column. Alright. So x1 is the column of the first queen. The x2 is the column of the second queen. Now we need to check that the second queen is not threatened, or does not threaten the first. So then we iterate over the column for the third queen, and then we check the threat that the third queen is not threatened by the first 2. We already know that the first 2 don't threaten each other. So we only need to check that the additional queen does not threaten the previous queens, and so on. At each step, we check that the additional queen does not threaten the previous queens, and the previous queens are already fine. And so this is the entire code. And then we output the columns for the queens that we found. The result is going to be a sequence of integer, because we yield a sequence. So each of our containers is a sequence. So all the types here are sequence, and the result is also a sequence, but the type of element is different, is sequence of integer now. And we just check that there are 92 solutions. We know that there are 92 solutions. Now, let's generalize this example to solve n queens problem, that is n by n board with n queens. And we do the same thing. Notice here we had hard-coded that there are 8 queens, and all this code has to be now generalized, which is done in the same way as before by introducing recursion. So how do we do that? So again, let's rename this to column, because I prefer to think about this as column, actually. So we define a function that is going to be the recursive function that adds another queen. And we have our previous queens, and it finds all the possible ways of adding another queen. And so that's going to be our solution. So n queens is going to be calling n queens partial on the required number of queens, and initially we have no queens already selected. And so this function says I want to add this many queens, and here are the previously selected queens. So we do the same as we did before. So X is going to be the column of the next queen. Then we check that the next queen does not threaten previous queens. Then we find the sequence of the new queens and call, so these are the newly selected queens after the filter line. So after this line, we are sure that the X is an admissible column for the new queen. So this is going to be the sequence of the queens we found, and we call the same function recursively, saying now we need to add m-1 new queens, and here are the queens we found so far. So rest is going to be a sequence of integer, and we append that sequence to the x. The x is being the queen we found, and then we're done. And so to verify that this is correct, I run the test for 8, 9, 10, and 11 queens and check the length, and it is known how many solutions there must be. Look at this page here that I found. Nobody really knows how to compute these numbers without enumerating all the queen positions. These numbers seem to be very hard to predict otherwise. So this is how we solve problems like permutations and traversing a solution tree and filtering out solutions that are undesirable in some way, and finding the list of all solutions. Notice just a comment here. In all these examples, functions that are recursive are not actually tail recursive because the recursive call occurs in the for yield block, and it's, in other words, inside some deeply nested flatMap somewhere. All these are translated into nested flatmaps. So if you look at this also, this is a recursive call. You see this little symbol here, so that is the IntelliJ telling me that it's a recursive method. But the recursion is not tail recursion. It occurs on the right-hand side here, and so there is some more computation that is being done after this call. And so it's not a tail recursive call. It's not the last computation being done. The tail recursive call would have been if the result returned by this function is the result that the entire call here returns, but that is not so. After this call, there is more computation to be done. So this is just a short comment here that these non-tail recursive functions are certainly not great in terms of safety, because if for any reason you need a large number of recursive calls, that will blow up the stack and give you Stack Overflow exception. There are ways of making this stack safe, but this is out of scope for this tutorial right now. We will talk about it in a later tutorial, how to make monadic recursion stack safe. It is slightly more involved than usual recursion because the recursive calls occur in a for yield block under monadic flatMap context. So that I will discuss in a different tutorial. So the last example for the list-like monads is a slightly different problem that I found quite interesting. I worked on it some time ago when I was implementing another open source project. I found that I have to transform Boolean formulas from distributed normal form into from disjunctive normal form into conjunctive normal form. So CNF is conjunctive normal form. And I found that this transformation is very simple if you formulate it in terms of the list monad. So let me show you the code. It's really I'll explain now what it means to transform between these normal forms in case you're not familiar with the Boolean logic. It's not difficult at all. It's just terminology. So what does it mean, the conjunctive normal form? So it's all about Boolean formulas like this one. So we have Boolean operations, or, and. So these are Boolean operations. And the Boolean formula in general can have any combination of these Boolean operations. Now we say that the conjunctive normal form is when the formula has this shape. It has some parentheses that are connected with and inside the parentheses there's only or. So there's nothing, no and is allowed inside the parentheses. No or is allowed outside the parentheses. So that is how we define the conjunctive normal form. A disjunctive normal form is the opposite. Inside the parentheses, the and only is allowed. Outside the parentheses, the or only is allowed. So these are the normal forms. And why are they important at all? The reason is any Boolean formula can be transformed into one of these forms, into both actually, whatever you want. The reason is there are Boolean identities, for example, the or and the and operations are distributive, so you can expand the brackets or the parentheses. So for instance, if you imagine, let me just make a little comment here so that it is more illustrative. So this, imagine that you replace or with a plus and you replace and with times. So that becomes an algebraic expression that you can transform by expanding the parentheses like an ordinary algebra. And then you can again replace the star, the multiplication, with and the or with, sorry, the plus with an or, and you put parentheses around this, and then you have a valid transformation of Boolean formulas. So this is, you see on the left, we have conjunctive normal form, because on the left hand side we have only OR operations inside parentheses, which are disjunctions, and conjunctions, which are AND operations, are outside. So the simple expanding of brackets or expanding of parentheses in the sense of ordinary algebra is what transforms one of these normal forms into another. So in this example, we will implement these transformations. We'll implement a transformation that corresponds to expanding brackets as a symbolic computation. In order to do this, we need to represent the formulas in some way symbolically. So we will do this by using sets. So let's use a type parameter t as a type that represents individual propositions in the Boolean formula. We won't do anything with that value. It will be symbolic for this reason. We just manipulate sets of these values of type t. And so in our representation, the normal form already forces us to have this structure, that there is a one or more, or actually 0 or more parentheses, and outside it's always the Boolean AND, and inside is always Boolean OR. So all we need to say is there's this set that has A and B in it, and there's this set that has C, D, E in it. The order, of course, is immaterial because A or B is the same as B or A. So sets are sufficient to represent this. And then we have a set of these two. So the outer set will be implicitly the Boolean conjunction and between these. And the inner set will be implicitly the Boolean disjunction between these. So that is going to be our short representation of the Boolean formula. So now let's just briefly consider what would be the true and false values in this representation. The value true is the empty conjunction, which is a conjunction of no parentheses, and that's the empty set. And the value false is an empty disjunction, which means we do have one set of parentheses, but there is nothing inside it. So that's a set of a single empty set. Now, the disjunctive normal form has the same representation in terms of data type. It's still set of sets of T. But it's just that the outer set now is the disjunction, and the inner set is conjunction. So because of this, the true and false are represented in the opposite way. So the true for this DNF is the set of empty set. That's if you're wondering why is it that empty conjunction is true, well, conjunctions are a monoid. So if you have some non-empty conjunction and you imagine that you have a conjunction of that with an empty conjunction, that shouldn't change anything. And so that's why the empty conjunction must be true, because the conjunction of true and X is X. The same as with false. False is the empty element for the disjunction monoid. So that's why false is the empty disjunction. So now, as I just showed you, it is easy to convert one into the other. You just need to expand brackets. So let's see how we can expand brackets. So let's just define these type constructors so that we can distinguish them more easily. The equality we just define this for convenience to compare the results. We want to run tests and we want to convert one into the other and compare results. So these are our representations of true and false, as discussed. So let's think about how we can expand parentheses or brackets here, for example. So we have a set of sets and we need to prepare a set of these sets out of them. So in order to do this transformation using a functor block, let's go like this. So x goes over this set, y goes over that set, and then we need a set of all sets that has one x out of here and one y out of here, right? So A, C, A, D, B, C, B, D. So that is easily accomplished. We have x from the first set, y from the second set. We just make a set that concatenates x and y. And so that's going to be the result. So if we just had two sets of parentheses, then we would write code like this. So now we need to generalize this code so that it is applicable to any number of parentheses, not just two. And we do it the same way that we generalized before. We write this code once and we use a recursive call. So let's do that. So the trick I'm using is that I need to check that the set is empty. But actually, I can check that. I can do what I did in the previous code examples, check that it's empty, and if not, I take the head. A slightly more visual and clear way of writing the same code is to use head option. So head option is defined on the set. So remember, v is the name of our data element inside the case class. So that's just our set of sets. We take a head option. The head option is going to be a set, or rather option of a set. And we match that. If there's nothing, that means we have a false. So we could have put this CNF false here, actually. Just to be more visual. Then we have the case when it's not empty. So then we have the first clause. We need to let x go over the first clause. And then we need to do a recursive call on the rest. So in this example, we're just 2. We need to go over the second one. But actually, in the recursive call, we would have more than one y in here. So let's take all of these y's. It's going to be a set. Y are all other terms that are converted to CNF by the recursive call. And so now we have x, which was chosen from the first set of parentheses, and all the y's is the rest of the CNF that was computed by the recursive call. So now we just need to concatenate these sets, and that's the result. And that's actually the entire code. So that's very simple. In order to run tests, we need to actually simplify things, because it turns out that simply expanding brackets will not produce results that are identical. Here's an example. If you have this kind of thing, this kind of Boolean formula. It's actually the same as this Boolean formula. Because this entire formula is true only when this is true. When this is true, then here we have true. We don't need to compute anything else here. We already have true in this set of parentheses inside here. So this can be just ignored. This can be simplified away. It is unnecessary to compute any of this. So this simplification can be just made by saying, well, is there any clause, well, these are called clauses, is there any clause that is a subset of another clause? So for example, this clause is a subset of this one. If so, then we can ignore this larger clause, and this is what this code does. It sorts the clauses by size, and then it finds what are the clauses that are subsets of another, and then if so, we ignore the larger clause, we just do the previous, and if not, we don't ignore it. So this is the code that simplifies using a fold. And these are tests. So for instance, this is the example. And actually, another interesting property is that this function is its own inverse. If we convert from DNF to CNF and then we want to convert back, we can use the same function to convert back. And this is so because expanding brackets is an operation that doesn't really depend on what operations are in and out of the brackets, as long as they're distributive. And they are distributive in the Boolean logic in both directions. And so it's the same operation, DNF to CNF. It's the same as CNF to DNF. It's its own inverse. And the test verifies that. We go DNF to CNF, and then first we convert this, and then we convert back, and it's the same thing. I would like to add some more examples of linear algebra manipulations to illustrate certain properties of the functor block. These are examples taken from the standard Scala library documentation. I rewrote them to be slightly more functional and clear. So the first example is to compute a transpose of a matrix. So in the matrix is represented as a sequence of sequences. And the result is again sequence of sequences. So how do we transpose a matrix? It's actually not so simple. Because, for instance, the first sequence in the result must be the sequence of all first elements of the sequences listed here. The second sequence in this result is the sequence of all second elements of these sequences. So how do we get all second elements of sequences? We need to know the index 0, 1, 2 and take that by index. So here's what we do. We define this index as an iteration here going over all indices of the first sequence in this sequence of sequences. So indices is a standard library function that returns a range such as 0 to 0 until something, 0 until length. So then once we go over these indices, what do we yield? We yield another 4 expression, it seems. In other words, we yield a sequence that is computed in a different way. How is it computed? We need, for example, here, the first sequence we need to return is a sequence of elements at index 0. So that's what we return. Let me rename this back to I, perhaps. when I here is 0, then we return a sequence, because the for yield returns a sequence of whatever you yield here, a sequence of 0th elements from xs, where xs goes over all of these. So in this way, we return a sequence of 0th elements of these, a sequence of first elements, second elements, and so on, as I goes over the indices. So you see, in order to do this, we had to put a for inside of a yield. And the result is not easy to read. This is a bit of a complication. So nested fors, either inside of a yield or inside here, you could put a for also inside here. It's harder to read and probably easier to refactor in some other way. So for instance, to make this a function that depends on I and XSS, and to put that function in here and make it more clear what exactly is being computed. But that is the core code, and that can be refactored when necessary for clarity. That's how it works. Transposes this into this. The second example is to compute a scalar product of two vectors. So we use the zip function. We have two vectors, or two sequences generally. And notice I'm using the numeric type class in order to have the sum, and I do this import so that I now have syntax. I can do star multiplication on the numeric type. You see, x is a numeric type, n, but I have multiplication on it, I have addition on it, because it's from the numeric type class. So the zip will create me a sequence of tuples, of pairs. So now for each tuple, I can write syntax like this. I can put a tuple right here. I yield the product, so that means the result, this entire for expression inside the parentheses, is a sequence of these products. And now I take the sum of all these products. That's the scalar product of two vectors. This is a test that it works correctly. And finally, I write matrix product. So again, the matrix product is kind of difficult because it has to be a yield that has a nested for, but this is how it works. So first of all, we transpose the second matrix, and then we take the scalar product of one vector from the first matrix and the one vector from the second matrix, and we put that into the resulting matrix. So that is, I'm not going to go into mathematical details here of how to compute matrix product, but this is the way that you can use the for yield block in order to iterate over these data structures. It's not particularly visual maybe, but at least there's no way to make an error in terms of indices or anything else. So that's an advantage. The next type of monads we are going to consider is the pass-fail monads. The examples are option, either, try, and future. So as I already mentioned before, pass-fail monads are containers that can hold 1 or 0 values of some type. Usually that is interpreted as success or failure. So if you do hold a value of type A, then you have success. You have successfully computed it. And if you don't, then you have failed to compute it. That's how it's usually interpreted. And these containers usually have special methods in order to create pass and fail values. And, an example of this is a try, a good example. Try has methods to catch exceptions. If exception occurred, then it will be a fail, and if it didn't occur, then you would have a value. So that's a typical pass-fail monad. Here is a skeleton or schematic example of a functor block program that uses try. We have some computations that might throw exceptions, so we put them into try. Then we say, well, x is from this. And what does it mean? Well, this container can have at most one value inside. So actually this is not an iteration at all. Unlike what we had in the list monads, this is not an iteration. This is, we're binding x as a new name in case that this is a success. If it's a failure, then there's nothing to bind. So this entire functor block will collapse to the failure. Remember that when the collection or the container on the right-hand side has 0 elements, then the entire for yield or functor block computation collapses to a 0-length container. This is exactly what happens if this computation here were to fail. If it doesn't fail, we can continue, compute something else. In this line, nothing can fail, provided that f does not throw an exception, of course. Here we can filter. If this returns false, then again the entire functor block will collapse to a 0-length container, so to speak. If it does not collapse, then we continue with new computation. Again, here this function could throw an exception. If so, then the exception will be caught and the entire thing collapses. When this entire thing collapses, the result is still a try, so the result will contain information about the failure. It will just contain no value of type A, so there won't be any value of type A in that case. And so on. So this is how we write code with the pass-fail monads. We keep assigning new variables here and hoping for the best. So the only way that we can yield a value here is when all of these computations are successful. So there's no failure in any of them. If so, then we yield a value of type A, and the result is therefore of type try of A. Now, the same rule holds that the right-hand side of the generator lines must be the same type constructor. But the type of these values could be different in each line. The type of values held by the container may be different, but the type of the container itself, the type constructor, must be the same. Or at least it must be some superclass. In Scala we have inheritance, so this could be used to have a superclass, and that is used for sequences. You can have different subclasses of sequence, but that must be somehow convertible to the same superclass. So another important thing to notice about pass-fail monads is that the computation is really sequential. So until this is done, until this computation is finished, there's no way to continue. We have to have this x to continue. Until this computation is done, and if it is successful, of course, there's no way to find a z, and so we cannot have an x here until this, unless this is successful. So this is really a sequential computation. We cannot continue usually with the next line of the computation until the previous line is done. So this is true even if we have the future functor. And the future functor schedules computations on different threads, and these computations could be proceeding in parallel, but still the computations are sequential. We'll see an example about this. So once any computation fails, the entire functor block fails. So remember, the number of elements in the entire collection is going to be the product of the number of elements in the generator lines. And so if any one of them is 0, then the entire thing collapses to 0. So there are going to be 0 elements in the result. In other words, it's going to be a failure. And if all the computations succeed, if there's no failure in any of them, so for option, failure means none. For either, failure means a left. For try, there's a failure constructor. For future, there's a failure constructor. Only when all of them are successful, then this entire functor block will have a value as a result, just one value. Also, filtering can make it fail. So the benefit of using the for yield syntax with a type constructor such as option, either, try, and future is that you don't need to write code with nested if, else, or match case expressions. You could have written this code with just match case. First you compute this try, then you match the result. If it's successful, then you get an X. Then you compute this. Then if this is successful, then you compute this, and so on. And you match on the result. So it will be a bunch of nested if, else, or a bunch of nested match case. That kind of code is hard to read, hard to modify. This is kind of a flat-looking code that is easier to read. And so you see, this has to be done, this has to be done. The code is logically flat. That is the advantage. It's easier to understand, easier to read. Of course, you have to get used to the syntax. The type constructors, I'm just writing out again that these must be familiar to you by now. These are disjunctions. So the pass-fail monads are typically disjunctions. The try is equivalent to an either, where the type Z is throwable, which captures exceptions. And then there is this data type A. So the typical reason we use these monads is we need to perform a sequence of computations. Each of these computations might fail, and we cannot continue if one of them fails. We have to report the error somehow. So we just make this explicit. We return an error value, which is not a crash. It is not some kind of exception or error situation. It's a value that captures the information we want to give about what happened and why things failed. And so that's the typical use of pass-fail monads. Let's look at some worked examples. So the first example is to read Java properties. So Java properties are strings which are held in the system dictionary of key-value pairs. So you have a key, which is a string, and a value, which is a string. So here's an example. We have some properties, and we want to compute something. For example, for a client, we want to find out which corporation the client is working for. For that corporation, what are the orders that were posted? And then for the order, we want to have the amount, or something like this. Now, the Java API is such that you can say get property. When you do get property, that returns a string, but actually it could return null if this property does not exist. And so in Java, this is the usual reason for null pointer exceptions. So some function returns null, but you didn't expect it. You start calling methods on that, you get a crash. So in order to avoid this and make it safe, let's put this inside an option. So the option type has a function that you put an option of something, and if that something is null, then you will get an empty option. Otherwise, you would get a non-empty option. So that's a very convenient function. Whenever you have some Java API that can return null in order to signal that something wasn't there or something was incorrect, wrap it into an option like this. That becomes safe. And now the code we write looks like this. First, let's say somebody gives us the client name. We want to return the amount of the order. Now, it might be that this client is not found, or the corporation is not found, or orders is not found. In this case, we cannot return the amount. Let me rename this function for clarity. I cannot return the amount in this case. So I will return an empty option. Otherwise, I will return a non-empty option with the requested amount. So this is the idea. I always return a well-defined value. Just that sometimes this value will be empty, or it will not contain the data that I was supposed to return, because I can't return that data. And so I write a for yield with these values being strings. But because this is a monadic block, whenever one of these is null, this entire block will collapse to an empty option. So I can write the code as if everything is good. So this is the so-called good path or happy path. But I know that whenever something is null here, either the corporation's property does not exist or order's property does not exist, then this entire for yield block will collapse into an empty option. So I'm safe to write code here. The last line, I'm trying to convert the string value to integer. Now this string value is guaranteed to be not null, but it could be incorrectly formatted, so its conversion to int might fail with an exception. No matter, I wrap that into a try. So after that, exception is going to be caught, and then I convert that to options. So there is this helpful method to convert try values to option. So if try had failure, then I would have an empty option here, and then everything will collapse. I'll return an empty option. So you see, this code has no if-else. It looks very linear, and yet it's completely safe. All the errors are handled. Invalid non-integer values even are handled. They're going to be ignored. And so the test is that if I want the order amount for client 3, there is no client 3, and I get none. The second example is to obtain values from computations using future. So this is an interesting example. In order to work with futures, I make this import just for simplicity. So imagine I have a long computation. Now I'm going to compute something not particularly useful, maybe some kind of long sum with cosine functions and whatever. It's not particularly important. I just want to have a computation that takes time. In order to save time on this computation, I want to make it in parallel. So I put this computation into a future, and I'm going to try to compute them in parallel. Now, here's the code I write. I have this auxiliary function time, which will return me the result and also the time it took to compute the result. So how do I compute the result? Well, I have a for yield, which uses the future. So the right-hand side of these computes a future of double. And therefore, the left-hand side is double. So the type of the container in this for yield block is future. It must be the same type throughout the container. So that is future. And the result type is going to be a future double as well. And so this looks like I'm performing first a long computation, which is going to be in the future. When that computation is done, I perform another long computation using that value as input, which will call this function and create a new future. And that future will depend on this x, because the computation uses the x or the c here. And so I cannot really start this computation until this one is finished. Putting futures in a for yield block will sequence them, in other words. First, it will wait until this future has done its computation and returned its value. And then we'll put this value in here, call this function, and start a second future. Wait until that is done, put this here, and wait another future. I should return z, probably, to be slightly less useless for this block. In any case, the result is that these futures are sequenced. One of them waits until the other is done. Now, imagine that these computations were not depending on each other. Well, here they do. This computation depends on this x here. Imagine that that weren't the case. If that weren't the case, let's say we have 3 computations and these parameters are known in advance, then we could have started all of them up front. So look at this code. So we create 3 futures, so all of these are of type future. We create 3 futures, and in Scala, future is a funny type, because once you create a future, you already scheduled it to run. There's no separate operation to start it or to run it. Once you make a future, it means the system will attempt to run it already. There will be probably already a running process. So this means these 3 computations are probably already running by the time we are here. What do we do here? We make a for yield block, which is superficially similar to this one. We just put the computations in variables and put them here. So the result, however, is going to be faster, because all these futures are started at the same time. Yes, here you wait for them, but they already started all in parallel, so you would just wait less. You would first wait until this is done, and while you wait, maybe this is already done. So this second wait will take no time at all. And so the result I expect to be faster. So in this test, I'm printing how long it takes. And the typical output I got in my tests was like this. So the first sequential futures it took 6 seconds, and the second took 2.7 seconds. So this is not exactly 3 times faster, but it is more than twice as fast in any case. We were able to do this only because the 3 computations don't depend on each other. If they do, then there's no way to speed it up. It's just, there's no advantage in putting that computation in the future if you cannot do it in parallel, for this, at least for this test. Let's look at the other example, example 3, which is we want to make arithmetic safe, and we use the either type to return error messages. So that's a very common use for a disjunction type. So let's make this type that has either string or double in it. And string will be an error message of some kind, meaning that we cannot compute the double value. Strictly speaking, this is not a functor because it doesn't have a type parameter. So I'm just abusing, the either is a functor. I'm using the either functor, and I'm just specifying the type to double because this is going to be in my example. But actually this is a functor with double as a type parameter. So we could think about this as a functor, and that's what it is, how we are going to use it. So the idea is that if there is an operation that could fail, then we return a left with some error message. And if there is a success, then we return a right with that value. So if we already have a double, then we do an implicit conversion of that to the safe double by just putting a right on around it. And in this example, the only operation we're concerned is division. So we can divide by 0. We don't want to try to do that. We want to return an error message. And so that's what this function does, is a safe divide. It would tell me what I tried to divide by 0. So hopefully it will help me in my debugging. So that's the point of this example. So here's the code that I use. So instead of writing val x equals 1, I put everything in a functor block. And you see, quite unlike the things we did with sequences, these are not loops at all. These are not iterations in any sense. For yield is not a loop. That is an important point that I would like to make. There's no iteration going on necessarily. It's a monadic sequencing operation, rather. So we are sequencing computations that might fail. If they fail, we want to fail the entire computation, if any of the steps fail. So here is what we do. X is assigned to be 1. That's not going to fail because there's no division. Here is a division. Let's say I know it's not going to fail, but we still use a safe divide. And then we do this. So the result is going to be always safe double. So here, the right-hand side of the generator arrows is either of the type either already, is a safe double, or it's automatically converted to safe double. So safe double is a type of the right-hand side of this block. And here's an example where it fails. So we divide by 0. We do exactly the same things, but because this step divided by 0, the entire thing collapses. We never get here, and the result is a left of that. The last example for the pass-fail is to sequence computations that may throw an exception. So here we sequenced computations that could divide by 0, and here we just have arbitrary exceptions. So here is what we do. Dividing by 0 throws an exception for integers. It doesn't for doubles, it gives you not a number, but for integers it throws an exception. So imagine we have some functions that might throw an exception. We wrap all of this into a trie, and then we have code like this. And so this is completely safe. The result is of type trie of int, and we can examine the result to see that it's a success or a failure. So we do a match expression, and then in this test I know it's going to be a failure because I first, what did I do? f1 of 1, so I divide 2 by 1, the result is 2. Then I subtract 2 minus 2, the result is 0. And then I divide 1 by 0. So I know it's going to be a failure. But in principle, here you could have a case of success. And that's how you use the pass-fail chain. So you put everything into a trie. The result is also going to be a trie. So let me just add the type here for clarity. You don't have to write this, but for clarity I want to. The next type of monads I'd like to talk about are tree-like monads. So what are the tree-like monads? Here are some examples. These are type constructors defined recursively. And I use the short type notation so that it's easier to understand what's happening. So the binary tree is either a leaf or a pair of two binary trees. So that's a familiar type, perhaps. And because it's recursive, then this can be, again, either a leaf or a pair of two binary trees. And this also can be maybe a pair. And so this is a pair, and this is another pair, and that just keeps splitting until it ends with a leaf. Another possibility of generalizing this kind of construction is to say, well, actually, this is a functor. This is a pair of f and f. Let's say that the pair of f and f is a functor applied to f. Let's call this functor s, the shape. And so then it will be a s of f of a. Let's take arbitrary functor s, not necessarily just a pair. So it could be a triple. Then the tree would branch in 3 branches at each point instead of 2 branches. So we can just parameterize the shape of the tree by an arbitrary functor s. This functor could be actually arbitrary. It could be a list. Then you would have a rows tree, what's called, where the branching can be arbitrarily large at any point. Could be any functor. So that's what I call a S-shaped tree, where S is a functor-shaped tree. Another interesting example of a tree is when both the leaves and the branches have the same shape. So the leaf must have a pair, and the branches must be 2. And an analogous generalization is when you have functor-shaped leaf and a functor-shaped branching. So these are perhaps more rarely used, but I found them interesting to consider as examples. For all of these, you can implement flatMap, and we'll look at examples of how to do that. So here's how you implement flatMap for a binary tree with binary leaves. This is our first type constructor here. Sorry, this is the third type constructor here, the binary tree with binary leaves. So how do you implement flatMap? Well, let's first define the type. So the type is this. It's a disjunction. The first element of the disjunction is a pair of AA. So just follow the type here. The first element of the disjunction is a pair of AA. The second element, the second part of the disjunction is a pair of two tree functors themselves. So I call this BX and BY. Now we need to implement a functor instance for this, and I have my own type class here called semimonad, just for convenience, where I can define flatMap. So to define functor is pretty easy. Obviously, if you have a pair of AA, you just map both of them with the function f. And if you have a branch, then you recursively map each part of the branch in the same way. So flatMap works actually quite similarly, except for the leaf. If you have a leaf, the leaf has two elements, and so you have a function that takes the leaf and returns a tree. So now you have two trees. So you cannot have a leaf with two trees in it, but we can have a branch. And so we put these two new trees into a branch. Here's how we can implement flatMap for a functor-shaped tree. And here I make a more abstract formulation where I have actually a tree that's parametrized by an arbitrary functor. So that's a functor-shaped tree. So the leaf is just one element of type A, one data item. And branch is a functor S applied to the tree. So it's a functor-shaped branch. How do we implement the functor instance, and how do we implement the semimonad instance for this tree? This is a little involved, but it's just the syntax that's a little complicated here, because we need to parameterize by an arbitrary functor, and so the type constructor is this. So the functor S is fixed, the type parameter is free. The map works by matching, so if it's a leaf, then we map the leaf value with the function f. If it's a branch, then we use the map function on the functor s, which we should have because we assume that s is a functor. And the function we use to map is the recursive instance of mapping the same tree. Here is what we do. We're in this case. So if we want to map A to B, we map A to B over here recursively, and then we map over the functor S because we know it's a functor. And flatMap works similarly. If we have a function from A to FB, then this A is just mapped to FB by itself, and we have an FB. And this maps FA to FB recursively, and then the outer layer of the functor S is mapped using its own map function. So here's how it works. So we have a function f from A to the tree. If we have a leaf, then we just put that entire tree instead of the leaf, or as one can say, we graft the subtree at this point. And if we have a branch, then we map over the branch, because we have the outer layer of the functor S, so we map that, and underneath we use the recursive call to the flatMap. Here's an example of a non-tree-like type constructor. It is a disjunction of this kind, so it can have 1A, can have 2 A's, it can have 4 A's, and so on, all the powers of 2. Now this type constructor is actually not recursive, so it is not a tree-like type constructor. It is not one of these. It cannot be represented as one of these. And it is not a monad in the usual sense, or not a tree-like monad in any case. So a little bit more intuition about how flatMap works for a binary tree. So imagine that we have a tree that looks like this. And we need to flat map it with a function that takes A. So all of these are leaves of type A. And so the function f takes A and returns a tree of type B. Imagine that when we apply the function f to these 3 values of type A, we get 3 different trees of type B. So suppose that these are the trees we get. So the tree that has these 2 leaves, the tree that just has 1 leaf, and the tree that has these 2. So then what the flat map is supposed to do, it's supposed to replace A1 with this subtree. So instead of A1, we'll have this subtree. A2 with B2, so that's this replacement. A3 is going to be replaced with this subtree. So A3 used to be here. Now it's this subtree. So this is the result of applying flatMap to tree-like monads. It grafts subtrees in places of leaves. That plays the role of flattening. So actually, nothing is being flattened here in a sense of trees remain trees. Trees are not flat in the ordinary sense, and they do not become flat in any sense. However, what becomes flat is that we had a tree initially. For each leaf, we replace that with a tree, but we don't get tree of trees. Tree of trees is just equivalent to a tree. That is what it means to be flat. Not that the tree becomes somehow non-tree-like, but a tree of B can be seen as simply a tree of B. There's no need to say that we have a tree of trees. A tree is already branching enough. So that's what flattening does for trees. And typical tasks that tree-like monads perform are traversing a tree and replacing leaves by subtrees, or grafting subtrees at leaves. One example of doing this is transforming a syntax tree representing some expression, where you substitute sub-expressions in it. So if this is some expression tree, then you want to substitute sub-expressions instead of leaves. And that's the kind of typical tasks that a tree-like monad will do. So let's look at worked examples. The first example is to implement a tree of string properties. So let's take a look at that. So prop tree is going to be our functor. So just for simplicity, I'm going to put map and flatMap into this trait right there. We'll implement them in case classes that implement the trait. This is not necessarily how you want to do it, but if this is your own type, it's easy to do that. If it's not your own type, so that you cannot change the source code for somebody else's type constructor, then you need to do type classes and add map and flatMap or using type classes. I just want to make it shorter here. So what is this type? So it has a leaf, which has a value of a, and also it has a fork, which has a name, and a sequence of other trees. So it's a slightly different shape. So the forks are named, so there's a name, and it can have 0 or more subtrees here as a sequence. So it's kind of a rose tree with named branches. So how do we implement map? Well, if it's a leaf, we just map the value. If it's a fork, then name stays the same, but each of the trees is mapped with its own function. This is a recursive call, really. However, the recursion is hidden. It's not in the same function. It's a function on a different object, but it's the same. It's still recursive. flatMap. So if we are in the leaf, we need to replace value a with a different prop tree. We just graft that prop tree in place of the leaf. That's a standard thing to do. And flatMap for a fork is just mapping. So basically, this is our example of a functor-shaped tree. This is this example, where the functor s has a specific type. It is a product of a string and a sequence of a, or a sequence of trees. So that is just a special case of the construction of a functor-shaped tree. Right, so here's an example. We have a fork with named A1, and it has a leaf 1, a leaf 2, and another fork named A2 with leaf 3. Now, we can map on this tree with the function that adds 10. So then each leaf will get 10 added to it. The structure of the tree remains the same after map, because map doesn't graft anything, it just changes the values at the leaves. Now, let's look at this code. We want to look at the leaves and somehow transform leaves that are small. And small is less or equal to 1. So here's the code for this. So we say x goes over tree, which means that actually the value of x goes over leaf values, because that's the values in the tree that are being used. And then if the leaf is larger, we keep it as a leaf. Otherwise, we make a fork in it and call it small and put a leaf inside the fork. And so we yield that. So this code transforms a tree, the tree that we had here, this fork A1 and so on, it transforms into this. So the leaf 1 is the small. And instead of leaf 1, we have now a different tree, this one. Everything else stays the same. So fork A1, let me maybe format this so that it's easier to see. easier to compare the two different trees before and after the transformation. So the only difference is that instead of leaf 1, we now have this fork with extra information. So that's the result of transforming the tree. So you see, this for yield is a kind of a loop, but it's a loop over a tree, and it can transform a tree into a new one. So just to repeat, for yield is not really iteration. It's more like a general kind of operation that goes over your container, and depending on what the container is like, it can do many things. So for the tree-like monads, it's usually tree traversal. Exactly the same computation written by flatMap syntax instead of for yield is this. The second example is to implement variable substitution for an arithmetic language. So what do I mean by an arithmetic language? So imagine we have a symbolic manipulation program that wants to manipulate expressions. It can be a compiler, or it can be some kind of calculator program, or anything else like that. So that kind of program needs to work with a symbolic language that does some kind of computation, and let's say arithmetic. So for us, we're going to have a very simple language. The language is going to have variables and multiplication, and nothing else. It will have constants, integer constants. It will have variables with names, and it will have multiplication, and that's it. So to define this language, we define a disjunction. So basically this is the term. Let me write down maybe the short notation for this. Term A is int plus A. So int is one part of the disjunction, which is called const. The second part of the disjunction is the variable, which is called var. And the third part of the disjunction is mult, which is two terms. So this is the definition of the type. This is recursive. And you see this tree-like, except that we have this extra thing here. But that's fine. That doesn't really modify the structure so much. Just that the leaf now can have an extra information. So let's define map and flatMap, and this is trivial. I'm not going to go over it. This is the same structure we had before. And now let's implement variable substitution. So what does it mean? So suppose so expressions in this language will look like this: as a constant times var times constant times var, and so on. There's nothing else in this language except constants, variables, and multiplication. So we can do that in any order we want. And that's all. Now, there are two operations we can do using map and flatMap. Using map, we can modify variable names. So we can, for example, append x to every variable name. So here's what the result would be. Appending x to variable names. Second thing we can do is substitute variables. So for example, instead of variable a, we can substitute this expression. So we can substitute new expressions of the same language instead of variables. And that's usually what mathematical expressions do. Variables in mathematics are substituted with new expressions of the same kind. So that's what we're going to do here. So let's substitute variable a with this expression and the variable b with that expression. And we do it like this. So x is going to range over variables. Y is going to replace x. So we yield y instead of x. If we just said for x going to expression yield x, that's going to be the same unmodified expression as before. So we modify, we say y is that, and well, we just throw an exception here just so that I have some simple example. But basically, if the name of the variable is a, then we substitute this, otherwise we substitute that. So the result is correct. Finally, we come to the non-standard containers, or single value monads. They are not really single valued in the sense that they're not equivalent to a container with a single value. Container with a single value is identity monad or identity functor. It's just a container that has a value a in it. That's not what they actually do, but they are similar to that. They can be imagined or reasoned about to some extent, thinking that they only and always hold one value. Actually, the meaning of the single value monads is that they hold a value and also they have some kind of context together with that value. And when you do computations, then contexts play a role. They can be combined and they can also be used to do something. And usually for these monads, we have methods that insert a value, or well, a container holds one value, so that's necessary to be able to insert that value in there somehow. And also usually there are methods to work with this context. And we will now look at 5 examples of single value monads, and we'll appreciate the variety of what this idea can do, holding a value in a context. So the typical tasks that single value monads do are to manage extra information about computations as you do the computations along the way, and also to perform a chain of computations that have some kind of non-standard evaluation strategy. So in the first case, when we are managing extra information, the context is this extra information. In the second case, when we are chaining computations with some non-standard evaluation strategy, for example, asynchronous computation or lazy computation, then the context is that what makes the evaluation strategy non-standard. So it's not a value. This context cannot be just seen as a value in this case. It is kind of the way that we do computations, or extra effects, or maybe side effects that occur during the computation, or something like this. So we'll see examples of both of these kinds. So let's look at the first example. It's the writer monad. The writer monad is defined as this type constructor. Very simple. It's just a pair of a data item of type A and a value of type W, where W must be a monoid or a semigroup. So for this to be a full monad, W must be a monoid. And for this to be a semimonad, W can be a semigroup. To remind you the difference between monoid and semigroup, a monoid has a unit element or identity or empty element, which is a selected element so that you can combine it with other elements without changing those other elements. A semigroup does not have that element. It's just a set with a binary operation that is associative. So here in this tutorial, we can consider a semimonad as writer as well, because we're not necessarily so interested in the monad, full monad right now. And so we will assume that W is a semigroup. So this W will hold some kind of logging information about our computations. And logging information we should be able to append one piece of logging information to another, and that's the semigroup operation. So let's look at the code. So in this example, we have, so I defined a writer as a semimonad, where A is our data type, and S is a semigroup. And so that is just a pair of A and S. Well, I wrote S instead of W. Let me just make W out of this. Just so that I'm consistent with my slides. So we can easily define the instance of functor, and an instance of semimonad. Now, the instance of semimonad is just flatMap. So semimonad is a type class that just requires flatMap with a standard type signature. So how does that work? Well, obviously, functor works by mapping the value, but not changing the log. So log is this information that we logged about the computation. Now, the flatMap has this type signature, so when we do the flatMap, we need to take the previous value, which is already a pair of A and W. Then we map A to another pair of B and W. Now we have two W's. So we have fa.log and fb.log, where fb was computed like this. And so we combine the two log values by using the semigroup operation. So this is how we could use this in practice. Imagine that I want to record in my log some comments about the operation and the time that the computations began and the time that computations finished for the entire chain of computations. Not just for each operation separately, but for the entire chain of computations, I want to find the begin time and end time. Here's how I can implement this. I make a semigroup that has three values. So the semigroup type is a triple of local date time, and string. How do I define the semigroup instance? I need to combine two logs of this type. So the messages I combine by just appending them with some new line as separator. But the begin and end I combine in a specific way. From the begin, I take the first begin. But for the end, I take the second end, second y.end. Because I'm combining two operations, so the first log and the second log, and I assume that the first log occurred first. And so the beginning of this entire operation is the begin of the first log, while the end of this entire operation is going to be the end of the second log. So that's why I'm putting it like this. Now this is actually a semigroup, it is associative, but it is not a monoid. It cannot be made into a monoid. So my writer here will be a semimonad. But that's the use case. So that's what I want it for. So now I define, for convenience, a type constructor, which is the writer with this logs as a type. And I also define a helper function, that will do the logging. So I have a value, I have some message, and then I insert the timestamp into the log and the message. That's very easy. I mean, I just insert begin and end for convenience as the same timestamp, and things will automatically be adjusted as necessary once I combine this with computations made later. So this import is necessary in order to use this machinery with a semi-monad type class. And here's the code. So these compute things are fake computations that pretend to take time. So they actually wait for this time, but that's fine for this example. So you see, I'm logging, so I'm logging everything with a message, and the times will be automatically logged. So I first start with a logged int, so the integer value. So x will be integer. Then I add 1 to that x. That becomes my y, so that's going to be 4. And then I multiply by the 2.0, which is a double, so the result will be logged double. And I yield z in the logged functor block, so the result is of type logged double. So as usual, the right-hand side of the generator lines is always of the same container type, which is logged. This is the container type for this entire functor block. This is the functor. So these are computations in the context of a functor. This is what I call computations in the context of a functor. We write as if these are values we compute, but actually these are inside the functor. So everything is so as if we return a double, but actually we compute a functor parameterized by double. So logged double, that's the type of the result. Let me put it in here for clarity. And the result is 8. So it's 3 plus 1, 4 times 2. Now we checked what the log message is. So the log message is actually begin with 3, then there's a new line, add 1, there's a new line, multiply by 2.0. So these are our logged messages. And also, I can check what is the interval between beginning and end. And the test checks that this is about right. So it's 20 milliseconds, 50 milliseconds, and 100 milliseconds together. It's going to be slightly bigger, but anyway, not much bigger. So this is the example of using the writer monad. In our case, it was a semi-monad, actually, not a monad. Using the writer monad, we can easily make automatically logging computations with keeping track of wall clock time. The second example is the reader monad. So the reader monad is also to be thought of as a container that holds exactly one value in the context, and the context is some value representing the environment, some type E, which is given. It is read-only. You can read it, and it's always available for you to read. So this can be used for dependency injection or for passing some common parameters that you don't want to pass explicitly with every function. And dependency injection means that the computation within the reader functor, or with the context of the reader functor, take this as a parameter automatically. They don't depend on what it is, and then you inject it later. So that's how it works. Let's look at an example. The example will be that we have logged computations, and the logger is the injected dependency. So let's say it performs some kind of side effect. It's a function of this type, and we want to make computations that use this function, but we want to depend on this function as a read-only context. So somebody will give this to us later, but we want to write code now. So we use the reader monad, which is just the cat's reader. Now cat's reader is equivalent to this type, which is just a function from E to A. So for convenience, we define this type as a reader of log duration A. So we will understand this container as a container that has a single value of A, but that value depends somehow, or computations can depend on this logger function in some way. So let's make a constructor for convenience that will log a message. So this constructor now has a lazy argument x. So this syntax in Scala means that the function argument is lazy. It is unevaluated until the function evaluates it. So that's kind of automatic lazy parameter passing. And here's the code. So the log returns a reader with the log duration in it. So it's a function from log duration to A. First we compute this x here and we time it. So we compute the time it took to actually run this x. See, this I just say result equals x. Actually, because x is a lazy parameter, it is not yet evaluated until I do this. So this is when x will be evaluated, and this might take time. And so I compute that duration, and then I log it using the logger function, and I return the result. So that's my convenience function. So once I coded this, I can write code like that, like I did before, very similarly. Now I can do another thing with reader, which is usually called tell. Now tell is just a function that returns the injected dependency, or the environment, or the context. And this is just a reader of identity, which is a function from E to E. It's an identity function. So using that, you can always extract that dependency explicitly and use it in if you want. So here's how we do this. We say log duration is tell, and now we can use that. That's our logger function. We can just use it ad hoc if we want to. We don't have to do this because our computations are automatically logged, but we might need to use it for in some examples. So the tell is the usual function that people define for the reader monad. All right, so how is it going to be tested? I'm going to have a logger that just prints some message, how much it took in milliseconds. And then I'm going to do a run. So important, I already computed this result reader, but nothing has run yet. This result reader is a function from log duration to double. This function hasn't been called yet. I have written the code as if the computation is already done, but actually it isn't yet done. It needs to be run still. So monads of this kind usually have a method called run. And so this method takes a log duration and it gives me a double. And so that's what I have to do at the end. And so the result is this printout, as we expected. It's about 20 milliseconds, about 50 milliseconds, about 100 milliseconds. And then there is this extra ad hoc computation. Now, just one note here. So the usefulness of this technique is that you can separate this code from this code. You can combine these readers with each other. You can put result reader here on the right hand side of a generator line because it has the right type. Whatever is on the right of the generator line must be of type reader of something. As long as it's the right type, a reader of log duration and something, you can put it on the right hand side. So in this way you can combine several values of the reader type in computation. You can make a longer computation, and at the very end, once you have done all you need, you actually run it. At the very end, when you actually know what logger you need or what context you need, what dependencies you inject, you run it. So this is the advantage. You can separate injecting your dependencies from writing code that uses the dependencies. And this code looks like this dependency is invisible. Here we made it visible because we wanted to illustrate that you can, but you don't have to. If I remove this, it's invisible if you have this dependency. Your code doesn't get cluttered with it. So that's the advantage. A third example is an eval monad, which is something that Cat's library implements. We will implement a very simple version of it ourselves for purposes of illustration. The idea here is to perform lazy computations. In other words, computations that are not immediately executed. And so in order to do that, let's define this type. So this type is a disjunction. It either has a value that's already computed, or it has a value that will be computed once we call this function. Now, this function has a unit argument, so there's nothing we're waiting for, but we just haven't called it yet. And so there's no data that we need to receive from someone in order to run this function, but it's up to us when we want to run it. And so that's the point of this monad. It's either a value that's already been done, and then so-called it's memoized. In other words, if you try to compute it again, it's already there. Or it hasn't yet been computed, and then this is a explicit representation of a lazy value. Scala has built-in lazy values, but sometimes it's useful to have a more explicit representation. So here's how it works. So let's define a trait, which is eval. Like I said, the Cat's library already defines this with slightly different API, but I don't want to use their eval because I want to show how it works. The main function that it has is get. So get means give me the value. So eval is a single value monad, so it holds inside it a single value of type A. So get me that value. And if that value hasn't been computed yet, compute it and give it to me. Otherwise, if it's already computed, don't give it to me right away. That's the point of this get. And then we have a map and flatMap because it's a semimonad. It's actually a full monad, of course, because it's easy to put A into here. So pure would be very easy to implement. It has a disjunction, as we have indicated, A and 1 to A. So let's see. A is this one. It's called eval now. So it's already evaluated now. And the second one is a function from unit to A. So it's eval later. So it will be evaluated later. So to get what's already evaluated is trivial. To get what will be evaluated later, we'll just call that x. Let's call this f. No, call this, okay, I don't want to rename this, maybe. we just call that function on a unit argument and we get what we want. Implementing the map and flatMap is trivial, except for one thing. So for flatMap, we eval later, but what we eval here, we get. In other words, we don't postpone that evaluation anymore. We already postponed once, so we don't want to postpone twice. That's the point of flatMap. So a non-flat structure would be that we postpone the postponed computation. So that's kind of nested postponement. We want to flatten it. So we want to postpone exactly once, and so we postpone, wait for the unit, but once the unit is given, that's evaluated. It is not postponed anymore. That's how it works. Now we can define convenience constructor. So this is a pure, which just gives you an eval now. And you can have a constructor for later, which gives you an eval later, and it's just for convenience. See, I'm using lazy evaluated argument in the function. Just one little comment here. In the programming, software engineering community, these arguments are called by name arguments. Can't be more wrong than call them this. They're not by name. They're unevaluated or lazily evaluated. It's not the name that you pass. You pass an unevaluated expression that needs to be evaluated. You don't have to have a name for it, and often you don't. So they're not by name arguments. They're unevaluated or lazy evaluated arguments. Anyway, so what do? Let's again use our compute helper function that will introduce delays into computations. And here what we do, we can write a for yield block with all sorts of things in it. And on the right hand side, we can either put later of something or now of something. So that's how we will use this. In this way, we chain computations that are postponed and computations that are not postponed. So we can combine them very easily with very clear organization of the code, and the result is again eval int. So this result is probably postponed, and we can get it. And when we get it, it will print things. So this is the output that you get. So when you create a value of this type, it doesn't necessarily compute anything. And you see this because this message is printed first. So this message is printed first. And only then these two messages are printed that we had here. So this might be counterintuitive, but actually when you do this, none of this is run yet. Again, this is a kind of monad that has non-standard evaluation strategy. It doesn't run immediately when you do a for yield. It will make these computations postponed. You have to run it. So the run for this monad is called get. And so that's when these two lines will be printed. So this could be a little counterintuitive when you work with these single value monads, because many of them encapsulate non-trivial evaluation strategies. Reader monad was of the same kind. Once you do this, nothing is done yet. The function is constructed, the function still has to be called, so that's the run call. Here it's the get call that actually runs the monad. The fourth example is continuation monad. This is not necessarily very clear what it means. I prefer to call it a callback monad, but continuation monad is a standard name for it. So I will go into detail now about how it works. The purpose of this monad is to chain asynchronous operations that register callbacks. So it's managing callbacks. That's the main use case for this monad. There are other use cases, but one of the main use cases is this one. So let's look at the code. The example I will show is using the Java input-output operations on files, using asynchronous file operations. So these are called asynchronous file channels, and they are asynchronous in the sense that you start reading the file and you need to pass a callback that will be called when it's finished reading it. So this is asynchronous. The code in this example is to read a file. So I've created a sample file, which is this one, which is very short. I'm going to read it into a buffer. I'm going to write the same thing that I just read into a different file, into this one. Then I'm going to read that file again and compare the results so that I verify that whatever I have in this second file is the same as what I had in the first file. So I'm going to read it into a second buffer and assert that the buffers have the same strings in them. Now you see how much code was necessary to get that done. All I did is to read one file, write the contents to another, read that contents, and compare with the first. Look at how much code I had to write using the Java. Look at this nested thing. It's a deeply nested combination of functions. This is a typical problem with asynchronous APIs that use callbacks. Callbacks get nested. Let's see how that works. The API is like this. You make a file channel, then you call the read function on it, which takes a buffer, then some parameters that are just, in my case, they're just 0. And then it takes a callback. Now the callback is a new object of type, or value, rather, of type completion handler. And the completion handler has two functions inside. One is called when there's a failure, and the other is called when there is success, when the file has been read. For the purposes of this example, I'm not going to handle errors. I'm just going to print that errors occurred. So I'm just going to concentrate on the happy path, on the success. So the callback for success is this. Now in my code, what I have to do is I need to wait until this callback is called. There's no way to wait for it. So the only way I can write my program is to write the rest of the program inside this callback. So that's how I get into a deep nesting. So the rest of my program is inside the callback. I'm closing the channel, rewinding the buffer, opening another channel, and then I call the write function on this other channel. The write function, similarly, takes a buffer and a completion handler, a new completion handler with its own callbacks. the failed callback, I print the message. The completed callback will be called when the second file is written successfully. There's no way for me to find out when that happens. So, right, because I already called the write function. The write function has finished very quickly, and then the file has started to be written after the write function has already returned. There's no way for me to figure out when this completed function will be called, this callback. Therefore, my entire rest of the program must be inside the callback. I close the output channel, I make another input channel, I read with a third callback. Print message when failed, completed, then the entire rest of my program must be in here. So, for example, I want to check that the bytes were correctly read and correctly written. I cannot really pass this information to somebody else outside of this callback unless I use global variables, global mutable variables, where I write some information, and a semaphore that somebody will have to wait for on a thread. This is horrible, very hard to write such programs. Or I need another callback that I will call here to pass this information. I could do this. If somebody gave me a callback, such as report result, I could put that result into the callback and call it. So somebody else will then have to continue writing this kind of code, that everything is inside the callback. Because of this problem, people usually say this is callback hell. There are all these callbacks that force you to write the rest of your program inside a deeply nested structure, like this. The continuation monad manages all this in a much better way. So let's rewrite this code by using the continuation monad now. The type of the continuation monad is going to be this. It is kind of not clear why this type is useful. But let's look at this and consider what it is doing. This type is a function that takes this as an argument. Now this function itself, this is a callback. This is a typical callback that we had in the completion handler. It takes some result or some input and returns unit. So a function that takes data and returns unit, that's a typical callback signature. So the continuation monad is something that consumes a callback. It's a consumer of a callback. That's how we can interpret this type. What can it do? What does it mean to consume a callback? Well, you can use the callback. The only way to use the callback is to run it. To give it a value of type A and run this function. And then whatever it does, you don't know, but that's what you can do. You can call it twice if you have several different values A. You can call it many times, or you can omit calling it at all if you don't get any values of type A. So that's what you can do with a callback. So when you create a value of this type, it means you have created code that will do something, possibly obtain one or more values of type A, and run this callback on those values. That's what the continuation monad is doing. So creating a value of this type, of this continuation type, means you have created your callback consumer or your callback logic. That's why it is so useful for situations where you need a lot of callbacks. You should not use callbacks like I just showed you in this complicated looking code. You should use the continuation monad. Here's how. So in our case, let's define this type constructor. The read and write functions for the Java NIO need to be adapted to this type. So let's create values of this type. And for convenience, we will allocate the buffer inside this function. So the read will take the channel and return a value of the monad type. So you see the monad type is this type constructor NIO monad of A. So we're going to use NIO monad of the pair of byte buffer and integer. We can use anything as a type parameter. Why? Because the idea is that the continuation monad manages callbacks or consumes callbacks that will be run on values of type A. And so the callback that we had in the previous code returned an integer, or rather it was called on an integer value. And so the byte buffer actually is another useful value that we want to pass on. And so we, by using this type, we make the API easier to use. So the callbacks in the Java API only take the result or parameter, which is a number of bytes read. You are supposed to have your byte buffers somewhere as global variables. It would be much better if they actually took data here as arguments, and that's what we can easily accomplish. So NIO read will be a function that returns the monad type. Therefore, we can use NIO read as the right-hand side of the generator. Here's how we do. We cont is a constructor of the continuation, which takes, remember, continuation is this type. So we need to create a value of this type. In other words, we need to write a function that takes this and returns this. So we write a function that takes this and it returns unit. So this entire thing should return unit. Handler is going to be this function because we defined it like this. So what does it do? Well, we allocate the buffer. For the purposes of this example, I'm cutting all kinds of corners. I'm just allocating a fixed length buffer for simplicity, and I'm ignoring errors. I'm just printing that errors happened. All of this can be done much better with more work. So in order to start understanding how to use it, we start with a simple example. So we allocate the buffer, then we call the read with this buffer, and we make a completion handler. There is no going around this API, but we only are going to do it once. And it's going to be much easier to understand, and nothing will be nested callbacks. So the failed we ignore, the completed will print something. Then we do all this, rewinding the buffer, closing the channel, and then we call the handler on the data that we obtained, on the buffer and the number of bytes read. So that's the call that will return unit. Remember, so the handler is a callback that returns unit. We can actually rename this for clarity, make it callback. And so we call this callback at the end, giving it the results we obtained. That is what a value of this type can do. It can take this callback, produce some values of type A, and call the callback on this value. So in our case, it's just one value. We're not going to call it ever in case of error. So we do exactly the same thing for the write. Now the write method needs a buffer and a channel as two arguments, and it returns an IO monad of integer. So that's very similar. Let's also rename this handler to callback for consistency. And it's exactly the same thing. So close the channel and call the results. So now let's see how this is going to be used. We open the channel to the file, and then we start writing the for yield, or the functor block. We do read. The result is a pair of buffer and result. Then we make another channel. We do a write with this buffer and this channel. That's a result. We make another channel. We do a read of that channel into buffer 2a, result 3a. Then we compute this is identical. Is the number of bytes the same and the string in the buffer is the same after copying? And we return, or yield rather, is identical. In other words, this is a Boolean value. Our entire for yield gives us an IO monad of Boolean. So this is a non-standard container. So none of this actually has been run yet when we do this, when we make this value. None of those operations have been done yet. We need to run the monad in order to run it. But how do we run it? Well, the run means that we take a value of this type and provide it with an argument of this type and apply that function to that argument. So we need to provide a callback of type A to unit, where A is Boolean, because we returned an IO monad of Boolean, so we need to provide a callback from Boolean to unit. Let's provide it. So the status is Boolean. So it's a function from Boolean to unit. So whatever we want, we can put in here, and then we run. That's what's going to print, and it does print exactly what we want at this point. Now, just one little remark here. You see, declaration is never used. Indeed, we never used this value. It is returned, so to speak, but it's not used. Let's just put an underscore here. That is the usual way that we indicate that there is a value, but we don't need it, and we put an underscore over there. All right, so that's how now our code has become flat in a sense. There is no nested anything. There is a bit of verbosity here because of all these options and so on. Well, you can always refactor that to be some function somewhere else. But basically, you can combine callbacks very easily like this. Now, nothing is so hard to understand except for the type of this thing, the continuation monad. The type of the continuation monad is hard to understand. You have to go through the steps. It's a callback consumer that will call the callback when the value is available, and that's what the run does. And you need to understand that flatMap does the same thing. So yeah, by the way, the implementation of flatMap for my continuation monad that's automatic. It's done by the Curry Harvard library. All right, let me go back to my slides. There's a last example, which is the state monad. The state monad is defined as this type, and it's used for doing a sequence of steps that update some state on the way. So each of these steps is a computation that returns some result, but also it has a side effect of updating some state. So recall this idea that single value monads are containers that hold one value and have a context. So the context for the state monad is this state, which is a value of some type S, as a fixed type. The type A is a type parameter of the container, but the state value S is a fixed type. And the context consists of this state and of the fact that you can update it as you go, so you can change it. And this is the type constructor. Again, just like continuation, it's not easy to understand why it must be like this. I will talk about this a little later. But first, let's see how it works. So one good example of using the state monad is to implement a random number generator. So a random number generator, or more precisely, a pseudo-random number generator, has an internal state that is updated every time you ask it for a new random number. So it gives you a result, which is a random number, but at the same time it updates its internal state. So a state monad allows you to do that in a pure functional way without any mutability, and also it has the same advantages as other monads, that you can combine things much easier. So without using the state monad, how would we do this? So imagine that all the functions are already implemented. So here's how. The PCG random is a very little package that I wrote. It has an initial state, so this state is some values, initial default state, or you can seed it with some other value you want. And then it has a function, which I called int32, that takes the initial state and returns a pair of some value and a new state. Then you would have to call this function again with this new state and get some random value y and a state s2. Now you have to call it again with s2 and get z and s3 and so on. So you would have to yourself keep track of these s0 here, s0 here, s1 here, s1 here, s3, s2 here, s2 here, and so on. And if you make a mistake, it's very easy to make a mistake. The types are not going to help you avoid this mistake. If you here say s0 instead of s1, the type is still the same. The compiler will not notice. So that is error prone and ugly. The state monad hides this. So it hides this, as they say, threading of the state, or keeping track of this new state every time. Here's how. So int32 is a function that takes internal state and returns a tuple of internal state and int. Yeah, so actually I need to interchange the order of these things just for clarity. int32 returns a pair of internal state and a random integer. So R&D is going to be the type that is the state monad. So this is going to be the functor in the functor block, R&D. And here's how we can use it. Now look at this code. The state is magically handled. All we do is as if we just have a random number function that gets us a new integer. And this is defined here. So it's the constructor of the state monad, which has this type, which is S to SA. And this is exactly the type signature of this function, S to SA. So this is the result. The result will be an R&D of string. Well, you see, R&D of int doesn't mean that it's a random integer. This is a constructor. This is a functor. The type of the value inside the functor can be anything. It doesn't have to be random. The randomness is only in this piece that returns random integers. Once you have those integers, you can make doubles out of them, and whatever you want, strings out of them. So just to warn you, not to confuse that somehow this type constructor itself makes everything random inside it. No, it doesn't. This is just a state monad. It just takes care of the state. And that's how you use it. Now you actually have to run. I'm using the cats state monad, which has its own API. It has a run. So you have to run it on initial state. And then the result will be something of which you need to get a value. And then that will be a tuple of state and result. So you take a second part of that tuple, and that's your result. So that's the API of cat's state monad. Oh. And you do this only once anyway. You usually accumulate a state value, combine them together. It's very easy to combine because monads are easy to combine. You can put a state value on the right-hand side of a generator arrow, and you have combined them, just like we did here. So once you're ready to run, then you perform the run and get all of this done. So just like the other non-standard containers, computing this value does not actually run any of these computations. It creates a function that will run the computations, and this function still needs to be called, and that call is usually run, the run method. So now we have seen how these different non-standard containers are used, and in what sense they can be interpreted as containers that hold one value together with a context, or how they perform computations in a context. In this slide, I will try to motivate why these types must be like that. You see, for the writer, maybe you understand why it must be like this. We need to log some information, so let's just put this information into this type here. But for these, especially these, this is kind of clear. You either have a value that's already computed or it's postponed. But these types are far from clear. Why are they like this? Why do these types embody what they do? So here is how I could kind of derive or motivate from first principles the choice of these type constructors. The main principle here is that we want to use flatMap in order to chain computations together. And so flatMap is the function that's going to be transforming some previous values to some next values in this chain of computations. So let's apply this reasoning and see what is the type signature of flatMap. And just by type reasoning, we will derive the correct types. Start with the writer monad. So this computation, and there's some information about it. The code we would write would be that first we have some value of type A, let's say some x of type A, and we transform it into some f of x of type B. So that's our computation that goes from A to B. At the same time, we compute some logging information of type W using the x. So what we have here, in other words, is a pair of functions, one from A to B and one from A to W. That is the kind of single-step computation that we want to chain together. So these are the things that we want to chain. Now flatMap should take this as its argument, because our principle is that we want to make it into a chain of flat maps. So in other words, this type must be the type of the argument of flatMap. But we know that flatMap has a type signature which looks like this, from A to writer B. Right? So in other words, more precisely, the argument of flatMap has this type. So flatMap has an argument of this type, and it returns a writer B. It has an argument of type writer A, an argument of this type, and it returns a writer B. So writer A, yes, we already have writer A always as the first argument. So in other words, this type must be the same as this. If that is so, we would be able to use flatMap to chain computations. What is the type writer B so that this type is equivalent to this one? In order to decide the type equivalence, we need to use the arithmetic Curry-Howard correspondence, as I called it. In this correspondence, the function types correspond to numerical powers. So A to B corresponds to B to the power A. A to W corresponds to W to the power A, and product is product. Now, using school-level algebra, we can simplify this, and we say it's like this. It's the identity. And by the arithmetic Curry-Howard correspondence, this is also the type equivalence. And so this is a type from A to product of BW. And so from A to product of BW. Hence, writer B must be product of BW. So in this way, we derived what the type of writer must be. Let's apply the same reasoning to the other monads, the reader, for example. We want a read-only context or environment of type E. So what is an elementary step in the computation? We have some x of type A, and we compute some value of type B, but we can use this R, which is the read-only environment of type E. In other words, our type of the elementary step on the computation is this. We repeat the same reasoning. If we want to chain these computations using flatMap, it means that the argument of flatMap must be of this type, but the argument of flatMap is of this type. In order to do that, we must have that these types are equivalent. This can be done when reader is the function e to b. Again, we use the arithmetic Curry-Howard correspondence. This type is b to the power of product AE. So this is just algebraic notation in the usual arithmetic, or I shouldn't say algebraic, arithmetic notation. This is just b to the power of a times e, which represents this type. And what we want is that this is something to the power a. And so this is b to the e to the power a. Therefore, we have the type EB. So again, a function type e to b is represented as b to the power e, with reversing the order of this. That is how the arithmetic Curry-Howard correspondence works for function types. I discussed this in the third chapter of the functional programming tutorial. Look at the continuation monad now. The continuation monad, or a callback monad, if you wish, it's a computation that registers a callback that will be called asynchronously. Asynchronously means it will be called later at some later time, or maybe not at all, or maybe once or more than once even. What is the computation of this kind? We take an x of type A and we call some function on the callback. So what does it mean to register a callback? We need to prepare some callback and pass it to somebody. Now this is the somebody who will take our callback, and they will return a unit usually. I mean, they're not going to call the callback right away anyway. So this function of registering the callback normally returns a unit. Well, it could return a different type, let's say indicating some error in registering the callback. But let's suppose for simplicity it returns unit. So the callback is of this type, because usually callbacks also return unit. So what is the type of this elementary step? The type is this. It's from A to a function f that takes a callback and returns unit. So if this function had type a to cont b, we would be able to use it in a flatMap. Well, this is clear. Cont b must be this. And we can generalize this to return a non-unit result type in case that this should return some kind of result, maybe error messages or something else. The callback could return more information than just unit. So maybe there's some error, maybe some other information. So usually the continuation monad therefore is defined as this type, where R is a fixed result type. Finally, let's look at the state monad. State monad is a computation that can update the state while producing a result. So what does it mean? Such a computation looks like this. First, we take some x of type A. We take the previous state of type S, and we produce some new value of type B using those two. At the same time, we produce a new value of type S from the previous state. So we at the same time change the state and we compute a new value. And while we're computing a new value, we can use the old state. And while we're changing the state, we can use the value x that was given to us. Therefore, the type of the elementary computation step is actually this. It's a pair of two functions from a and s to b and from a and s to s. So the first function computes a new result, and the second function computes a new state value. Now we repeat the same argument. This type must be the type of the argument of flatMap, in other words, this. So what is state B if this type must be equivalent to this? Let's make a computation. We again use the Curry-Howard correspondence. This type corresponds to this expression. We want it to be something to the power a in order to reduce it to this form. So we transform it like this, something to the power a, and we can also simplify it like this, something to the power a. Translating back to types, it means that this type is equivalent to this. In other words, A going to this. Or more simply, this. So state B is a type that must be this. So we have derived the type constructors for the monads from first principles. Just the principle was we have some elementary step of computation that deals with some kind of context together with a new value. And we want this elementary step of the computation to be usable under flatMap. In other words, the type of this elementary step of the computation must be of the kind A to FB, where F is the functor. That is the type of the argument of flatMap. So systematically, we demanded that the type was of that kind, and that allowed us straightforwardly to derive the types of these monads. You need to get used to these monads in order to be proficient with them, but I hope that this derivation kind of lifts the veil of mystery from the question of why are the types of monads chosen like this, and what is this context that they manipulate. Here are some exercises for you to get more familiar with using monads and to implement simple examples using set, sequence, future, list, or try, and state monads, as well as implementing semi-monad instances, which means simply implementing flatMap for certain type constructors. That concludes part 1 of chapter 7.